Hi everybody. So in this video, we're going to look at Euler's form of a complex number and how we can use this to convert between x plus iy form and modulus argument form. So we'll work through a couple of examples and then we'll try some exam style questions. If you want to work along with me, you can download a copy of this PDF from my website. I'll leave a link below. So if we take the x plus iy form for a complex number, and we should be familiar with this from year 12, then we can write this as an exponential, where z is equal to r, and r is the magnitude of a complex number, multiplied by e to the I theta, and theta is the argument. So r is the magnitude, and theta is the argument. And the argument ranges from less than or equal to pi to greater than negative pi. So throughout this video, I'm going to show you how we can write complex numbers in this form. If we begin with example A, to write this in exponential form, we need to use an argand diagram. That will help us work out the magnitude and the argument. So we've got a real part of 1 and an imaginary part of root 3. And we know the complex number originates from the origin, so it will be about here. 1 plus I root 3. Then to work out the magnitude of this, we can use Pythagoras' theorem. So r will be the square root of 1 squared plus root 3 squared, or just 3. So this will be the square root of 4, this will be 2. And then to work out the argument, we'll say this is the argument coming from the real axis. Then the tan of theta will be the opposite side, which is root 3, divided by the adjacent, which is 1. So the argument will be the arctan of root 3, which we can work out as pi over 3. So in exponential form, the radius is 2 multiplied by e to the pi I over 3. And this pi over 3 is the argument. Okay? If we look at example B, to go from exponential form to x plus iy, we need to use the modulus argument form, which we covered in year 12. And this is where we have the radius multiplied by cosine of the argument plus I sine of the argument. And we know that theta is 3 pi over 4 and r is root 2. So we'll substitute these in. We've got root 2 times the cos of 3 pi over 4 plus I times the sine of that same argument. And then to write it in x plus iy form, we just need to expand out these brackets. So we'll have root 2 times the cos of 3 pi over 4, which works out as negative 1. And then we've got root 2 times the sine of 3 pi over 4. And this will give us positive 1. So we've got the negative 1 as the real part, plus the 1, which is the imaginary part. So negative 1 plus I. And that's what we were asked to show here. Okay? So I hope that's given you an idea on how we can convert between the different forms of a complex number. Let's look at example 2. So in example 2, I want to show you how we can use the exponential form to raise this complex number to the power of 6. So we'll begin by converting this complex number to exponential form. We'll draw a quick argand diagram. We've got negative 2 root 3 on the real axis and negative 2i on the imaginary axis. So the complex number comes from the origin and it'll be about here. So we can work out the radius as 2 root 3 and 2. We'll use Pythagoras' theorem. So 2 root 3 squared plus the 2 squared, and we get the square root of 16, which is 4. And then to work out the argument, well, again, this comes from a real axis, but we don't have a right angled triangle here. So what we can do is we can work out this angle, we'll call this beta, and then to find the argument theta, we'll use angles on a straight line. So the tangent of beta will be the opposite, which is 2, over the adjacent, which is 2 root 3. So beta will be the arctan of 1 over root 3. So beta works out as pi over 6. So if beta is pi over 6, and the argument comes from a real axis, this will be negative pi plus that pi over 6. So the argument will be negative 5 pi over 6. So we've got a radius of 4 multiplied by negative 5 pi I over 6. And all of this is raised to that power of 6. And now we can use De Moivre's theorem, where we can raise this 4 to the 6 and multiply the argument by 6. Again, we covered this in year 12. So to multiply this out, we'll have 4 to the 6 times e, and then 6 multiplied by that argument times I. And we can simplify this, we'll cancel out these 6's. So we've got 4096 times e to the negative 5 pi I. And we can simplify this negative 5 pi. If we go from a real axis, we go negative pi, negative 2 pi, negative 3, negative 4, negative 5 pi. So we land on the negative part of a real axis. So this simplifies to make 4096 e to the negative pi I. And this is the real part of negative 1. So we can simplify it further as negative 4096. Okay? If we look at example 3, so now we've been given the complex numbers z and w both in exponential form. We've been asked to work out z divided by w and z cubed times w squared, and then to give our answer in x plus iy form. So if you want to give this question a go yourself, you can pause the video and come back when you're ready. Okay, so welcome back if you had a go. So if we divide 2e to the pi I over 3 by 3e to the negative pi I over 6, well, we can have 2 divided by 3. This will be our modulus of a magnitude multiplied by e, and then we can use the division rule of indices with these two. So we'll have pi I over 3 minus the negative. So this becomes a positive pi I over 6. We can factor out this I, so we get 2/3 times e, and we'll add the pi over 3 to the pi over 6, and we get pi I over 2. Now, if we've shown this on the eigen diagram, pi over 2 lands on the imaginary axis, so this will have no real parts. So we're looking at a point about here, which is 2 over 3i. So in x plus iy form, we've got 0 plus 2/3 I. Okay? And then for part B, we'll raise 2e to the pi I over 3 to a power of 3. And when we expand this out, we'll raise the 2 to the power of 3, and we'll get 8. And then we'll multiply this argument by 3, so the 3's will cancel, and we've got 8e to the pi I. And then when we square w, we'll raise the 3 to the power of 2, and we'll get 9. And we'll multiply the argument by 2, and we get e to the negative pi I over 3. We can multiply the 8 by the 9, and we get 72. And then because the bases are the same, we can just add these two powers. So pi take away pi over 3 will give us e to the 2 pi I over 3. Okay? How did you go with that? Let's try one final question. So in example 4, we have the complex numbers p and q, and we've been asked to write them both in exponential form, then to work out p divided by q, then to convert that into a plus bi form. So again, do you want to give this question a go? You can pause the video and come back when you're ready. Okay, so how did you get on with that? If we convert this to exponential form, we're looking at p, the radius will be the 9 squared plus the 9 root 3 all squared, square rooted. We can work this out and we get 18. The argument will be the arctan of the opposite 9 root 3 over, and this will give us pi over 3. So in exponential form, p is 18e to the pi I over 3. If we look at q, the radius will be the 3 squared plus 3 root 3 squared, all square rooted. And this will give us 6. The argument will be the arctan of the opposite divided by the adjacent, and this will give us pi over 6. So in exponential form, q is 6e to the pi I over 6. Then to work out p over q, we'll have 18e to the pi I over 3 divided by 6e to the pi I over 6. We'll divide the 18 by 6 and we'll get 3. And then we'll have pi over 3 take away pi over 6. This will give us e to the pi I over 6. And then for part B, to convert this into a plus bi form, we'll use the modulus argument form, then expand out the brackets. So we'll have 3 cos pi over 6, which is 3 root 3 over 2, and 3 sine of pi over 6, which is 3 over 2. So we'll have 3 over 2 plus 3 root 3 over 2i. Okay? Well, I hope that's given you an idea on how we can work with the exponential form of complex numbers. If you found that helpful, please like and subscribe, and you can download the full lesson and the PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link below.